All right, welcome back everyone. So continuing on with part two of this video, and again, this is getting pretty deep into some maths here, but hopefully if you've got a bit of a background in some of this stuff, you can try and understand it. Again, just try and follow the reasoning, and this is kind of what this higher level maths kind of looks like. Where we left off last time was we have come up with a formula for an infinite geometric series. So we found that if we start out with a number, multiply it by a common ratio, so there should be a plus AR here, multiply it by that common ratio again, etc. Add up all of those terms, we actually come up with this nice little formula. That starting number divided by 1 minus that common ratio that we're multiplying each of the terms by, given that that common ratio is less than 1 and greater than -1. Okay, so that was our first part of that video. If you did specialist maths, you will recognize this formula, or possibly even if you did general maths, you might recognize this formula for a geometric series. So now we're going to assume that E is a rational number. So this is what we call a proof by contradiction. We started out with this assumption. If E is a rational number, that means that by definition, it can be written as one integer divided by another integer. And we found that if we multiplied that formulation of E by B factorial, we will also get an integer. So we can see here, if we accept that E can be written as A over B, then B factorial times A over B must be an integer, because the B here would cancel out with the B down here, and we just end up with a bunch of integers that are being multiplied by one another, which clearly is going to be an integer. And what we then did is we substituted in our definition of E, which relies on the summation of an infinite number of factorials. So specifically, we were working with the definition that E was equal to the infinite sum from n equals 0 up to infinity of 1 over n factorial, which is written out like this. And we found that if we substitute in that definition of E into this formulation here and expand in a particular way, we're going to get b factorial times the first part of the summation to 1 over b factorial plus b factorial times the second part of the summation. And we showed last time that this first part of the summation must be an integer, because each of these denominators is going to cancel out with a part of that factorial. For example, b factorial over b factorial could be like 7 factorial over 7 factorial. If b was 7, then we would get 7 factorial over 7 factorial. Well, that's actually just going to be equal to 1, because everything up the top will cancel out with everything down the bottom. So what we have here is a bunch of whole numbers, bunch of positive integers that are being added to one another. So therefore, that whole result must be a positive integer, which means that the second part must also be an integer. Why is that? Well, if we accept that the thing on the left-hand side is an integer, and we found that that integer is equal to an integer plus something, then that second something must also be an integer. If we think about it, 21 is equal to, say, 19 plus something. If we don't know that that something is 2, we do know that that something must be an integer, because we can't have like a whole number plus a fraction that will give us a whole number. So these two things must be integers. So let's now focus on this second part of the summation. So we're going to consider this part here, okay? The second part of our formulation here. So let's take that thing. And remember, our entire proof relies on this being an integer. So we have here that we have this thing. In fact, we can give it a special label. Maybe let's call it x. So let's say that x, what happened there? Let's say that x is equal to b factorial times 1 over b plus 1 factorial times 1 over b plus 2 factorial plus 1 over b plus 3 factorial, all the way to infinity and beyond. This summation goes on forever. So what do we know about this thing? Well, one thing that we know about this thing here is that this thing must be larger than 0. Why is that? Well, because b is an element of the positive integers, right? So this thing here, this denominator, this is a positive number. We have a positive number times a fraction that fraction, quite clearly that will be a positive number. Maybe it's 1 over a really big number. That could be 1 over a billion. That's still like 0.00, a bunch of zeros, and eventually there's going to be a 1 there. It's larger than 0. In fact, every single one of these terms is larger than 0, and it's being multiplied by something that's larger than 0, so the result must be larger than 0. Okay. So that's good. What else do we know about this thing here? Well, this is one thing that we could do. We could try and expand the brackets on this summation and see if we can simplify it down any further. One thing that we should know about b factorial, and I'll do this a little bit lower down. In fact, I'll just do it right here. Let's do it over here. B factorial. B factorial is going to be equal to b times b minus 1 times b minus 2 times b minus 3, etc. In this infinite series of factorials, or effectively infinite series of factorials. So what you might notice is if we were to expand the brackets here, we'd have b factorial over b plus 1 factorial. That b plus 1 factorial would be equal to b plus 1 factorial, sorry, b plus 1 times b minus 1 times b minus 2, etc. So this is what I'm saying. B plus 1 factorial, sorry, is going to be equal to b plus 1 times b minus 1, etc. If we were to expand this, then almost everything that's in that expansion would cancel out, leaving behind just the b plus 1. So we can see that this would be equal to b plus 1, this first term here. So 1 over b plus 1, because every other part of this expansion would cancel out. And in the same way, this second fraction here, if I go expand out like this, b factorial divided by b plus 2 factorial, then the b factorial up the top would cancel out with a lot of this. So b plus 2 factorial, that's equal to b plus 2 times b plus 1 times b factorial. That b factorial at the top cancels out with this b factorial down the bottom, leaving behind b plus 2 times b plus 1. And in the same way, this next part of the this infinite sum is going to be equal to b plus 1 times b plus 2 times b plus 3. And now we can see a bit of a pattern emerging. Okay, so what can we do about that? Well, one claim that I'm going to make for you is that this overall series of terms that are being added together here is going to be strictly larger than, sorry, it's going to be strictly less than, I should say. It's going to be strictly less than 1 over b plus 1 plus 1 over b plus 1 times b plus 1 times 1 over b plus 1 times b plus 1 times b plus 1, etc. Now, why is this the case? Well, we can see here, the thing that I've written up here, 1 over b plus 1 is quite clearly the exact same as 1 over b plus 1, so obviously they are going to be equivalent to one another. This next term here, we have 1 over b plus 2 times b plus 1. If we think about, in terms of fractions, if the denominator is smaller, then the fraction is quite slightly larger. So, for example, 1 over 3 is a larger number than 1 over 4. Like a third is larger than a quarter. So, for example, this term here is going to be larger than this term here. And in the same way, this term will be larger than this term here, right? Okay, now this is where the magic comes in. So remember earlier we came up with this formulation for an infinite geometric series. That's actually exactly what we have right here. What we have is a geometric series. This overall thing here is a geometric series for which the starting term is equal to 1 over b plus 1, and the common ratio that we're multiplying each term by in this formulation. Ooh, what happened to this? Hang on, something's happened to my pen. All right, let's see if I can fix up this. Not sure if my pen died or what. Okay, so the common ratio in this series, there we go, is also equal to 1 over b plus 1. So we can see here, if we think about this as a geometric series, the starting term is 1 over b plus 1. The second term is 1 over b plus 1 times 1 over b plus 1. So if we think about 1 over b plus 1 times 1 over b plus 1, we'd have 1 times 1 up the top, and b plus 1 times b plus 1 down the bottom. We get this. And then the next term is going to be 1 over b plus 1 times b plus 1 times b plus 1. So it's the same thing. Starting term, common ratio. But as we found up here, we actually have a formula for an infinite geometric series. So this infinite geometric series, as we now know, is going to be equal to the starting term, 1 over b plus 1, 1 over b plus 1, divided by 1 minus the common ratio. Here, 1 minus r. So let's write that down. 1 over the common ratio, which is b plus 1. All right, now how do we simplify this ugly looking fraction? Well, one thing that we might want to do is multiply the numerator and the denominator by b plus 1. Now, why might we do this? Well, it just makes things a little bit easier. So up the top here, remember, this maintains equality because we're doing the same thing to the numerator and the denominator. That's going to cancel that with that, leaving just behind 1. Now, if we expand the bottom part, this cancels out with this, and we also need to times it by the 1 over here. So we're going to end up with 1 over b plus 1, so b plus 1 times 1 minus 1, all right? And if we have a look at this fraction, well, this simplifies down even further. We have 1 over b plus 1 minus 1. We can just expand those brackets and we have 1 minus 1. That leaves behind 1 over b. Okay, so what have we found now? Well, we found that this expansion, right, like this expansion here, b factorial times 1 over b plus 1 factorial plus 1 over b plus 2 factorial plus etc. This overall thing that we've looked at here is, as we set up here, it's greater than 0. So it's greater than 0. And we've now found that it is less than 1 over b. Now, what can we say about this 1 over b thing? Well, b is a positive integer. That means it's greater than or equal to 1. So if we have 1 over a number that is larger than or equal to 1, we're going to have at the very most 1, and we're going to have a number that is larger than 1, but still positive. So this thing here is going to be strictly less than or equal to 1. So for example, this could be 1 over 2, could be 1 over 7, it could be 1 over 20. In any case, this thing will be less than 1, but it'll still be a positive number. So what do we find? Well, we're finding here that this overall expansion, right, right here is greater than 0 and less than 1. So what does that tell us? Well, it tells us that this is not an integer, right? This is not an integer because it's between 0 and 1. There are no integers between 0 and 1, right? Like it's a whole number. There's no integers between 0 and 1. So that tells us that this is not an integer. And this is huge. This is huge. This is our contradiction that we have found. So let's recap what we looked at here. We found that if e is a rational number, it can be written as an integer divided by an integer. Then, if we multiply that by the denominator, whatever b is, factorial, we should also get an integer. And we've just found that that thing would be equal to an integer if we use the definition of e plus whatever this was. But we found that that second thing was not an integer, and therefore we have actually reached a contradiction in our proof. So this is a contradiction. And what that tells us is if we start with the assumption that E is rational, then we encounter a problem. So therefore that tells us that E cannot be written as A over B, where A and B are rational numbers. This is impossible. E cannot be written as an integer divided by an integer. So therefore, by definition, E is not a rational number, which is to say it is an irrational number. Now, there you go. That was quite a heavy sort of video. So again, don't worry about understanding this entire thing. You could have skipped this entire video and it's not going to affect you in the slightest. You just need to kind of know the basic definition that E is a irrational number, and what that means. So it means that it can't be written as a whole number divided by another whole number, and it also shows us that that E can be defined using this definition here. That's also something that it's useful for you to know for methods, that E can be written as this infinite series of factorials. You don't need to know anything else. You don't need to know this geometric series definition. Of course, you do need to know these different types of numbers. You need to know this notation, like that E is an element of R. But if you can just try and understand the mathematical logic behind this procedure, I think that's going to really enrich your understanding of mathematics, and exactly how mathematics can be used to structure like an argument like this. As we can see, it's almost like a way of thinking, or a way of arguing a case. So it's the language of logic is being used here. And while proofs aren't part of the course for you guys, I think it's kind of useful to understand that everything that you're learning about in maths has a basis behind it. It hasn't just been invented out of nowhere. There is rigorous definitions that are being used in everything that we're looking at. So anyway, that was like a bit of a tangential video, basically in answer to the fact that I put a question on that homework task that was way beyond your level. This is what an answer to that question might look at. So don't worry about it too much. You can just, give a very brief explanation to that question and just move on the rest of the task. You shouldn't have too much trouble with. Like if you Google it, you should be able to find the answers to most of the stuff in there. All right, thank you very much for that, guys. If you have any questions or concerns about that task, just send me an email and I'll get back to you. Thank you very much.